We are on 4.2 Ionic Bonds, and this is the overview of the 4 topics we are going to discuss broadly. First, I'm going to talk about the main points of Ionic Bonds, and then in part 2, I will discuss from between A to E, predicting formulas of ionic compounds using criss-cross method, and drawing Lewis dot structures of ionic compounds for monoatomic ions, and then drawing what their lattice structures look like. I will use 3 examples of compounds to do this. And then we will look at how to name ionic compounds made with monoatomic ions, single atom ions, and then polyatomic ions. We will do a bunch of examples, practice questions, and then finally we'll look at properties of ionic compounds. So, main points. Ionic compounds are an electrostatic attraction, like I've shown over here, between an anion and a cation. Electrostatic attractions can occur between polyatomic ions or monoatomic ions. Either the cation or the anion, or both of them could be polyatomic or monoatomic, or a combination of the two. Generally, some people say electronegativity difference between 1.7 and higher is ionic, but for our class, let's go with 2.0 and greater. That is going to be considered an ionic compound. And we discussed the electronegativity scale, Pauling's electronegativity scale. All of that applies to this. The metal atoms donate electrons and becomes a plus charged cation, and the nonmetal accepts these electrons because nonmetals want to fill their valence shell and look like the noble gas that comes after them, and they form anions. And these are monoatomic ions that are made by a single atom. Attractions between oppositely charged ions are called electrostatic attractions. Please remember that that's what I have shown over here. Polyatomic ions are ions that contain more than one atom covalently bonded together, but they have a charge or a oxidation state just like cations and anions from monoatomic ions, like chlorine minus, Br minus, O2 minus kind of ions. Formulas for ionic compounds can be predicted using the criss-cross method. I will teach you what that is. Basically, you swap the numerical value of the oxidation state or the charge and swap it between opposite ions. Ionic bonds are electrically neutral because their total positive and negative charges equal 0. Ionic compounds arrange in repeating patterns called a crystal lattice. It's like a lattice pie. The energy needed to break or dissociate 1 mole, which is 6.022 times 10 to the 23 ions from an ionic compound, is called lattice energy. So this is their dissociation energy. We basically measure it as lattice energy. Once the lattice is broken, now ions revert back, transform back into their neutral atom states. They get back their electrons that they donated and go back to normal. Most ionic compounds are called salts. So, for example, sodium salts are all sodium-containing ionic compounds. Magnesium salts are all magnesium-containing ionic compounds. For example, Epsom salt is a magnesium sulfate. That is a polyatomic ion and a monoatomic cation. To name the compounds, you start with the name of the metal atom as it is, and then it ends with the name of the second ion. If the second ion is a polyatomic ion, you don't use a prefix. But if it's a monoatomic ion, you use the "-ide" prefix. For D block metals, when you write the name, you also state the oxidation state within parentheses after the metal name is written in, and inside the parentheses, you write the oxidation state in Roman numerals. Ionic compounds conduct electricity in their liquid state. Solids at room temperature, they have high melting points and boiling points, and they dissolve easily in water. And in the liquid state, they also conduct electricity. And electrolyte is a solution made of water and an ionic compound that conducts electricity. So Gatorade, you guys know electrolytes that people drink. Anything you dissolve, any kind of salt in water, you have an electrolyte. And I talked about lattice pi. Here's what it looks like. The plus and minus ions are interconnected in a three-dimensional structure that forms these crystals. We call it a lattice structure. So topic 2, we are going to look at how ionic bonds form. We are going to predict the formulas of ionic compounds using the criss-cross method. I will teach you what that is. It's a really handy-dandy technique. And we will learn to draw Lewis dot structures like we did for covalent bonds. And we only have to learn how to draw these structures for monoatomic ionic compounds. So you don't have to worry about it. And we will also look at what their crystal structures look like. You do not have to draw crystal structures. So let's look at the ionic bond formation between sodium and chlorine. Here's a periodic table with the metals and the nonmetals. So here is sodium and here is chlorine. And this is what the sodium atom looks like. It's in row 3 of the periodic table, N equals 3 shell. So it has 3 shells. The valence shell is 3, and it has, since it's in group 1, it has 1 valence electrons. And let's look at chlorine. It's in group 7 in row 3, which means it too has 3 shells. The third shell has 7 electrons because it's in group 7a representative element. So what happens is sodium donates its electron to chlorine, and now sodium lost its valence electron. So now its last shell is energy level 2, and it has 8 electrons. So it now has a plus charge because it lost an electron, and now one of the protons in the nucleus is no longer neutralized by that electron. So you have a +1 charge. And sodium now looks like neon. The valence, the noble gas configuration is neon. And then chlorine now looks like argon. And it has a full set of valence electrons in energy level 3. So let's look at the crisscross method to determine the molecular formula of NaCl. So you're going to write the sodium ion charge. So because the metal is always going to make a cation, you write +1 because it donates the electrons that equals its representative A group number. So it's in group 1a, so it makes +1 ions. For chlorine, it's in group 7a. Nonmetals, their ion charge is a negative charge, and it's equal to how many electrons they need to become 8. So we talked about this earlier in the periodic table unit 3. So if you're in group 7, your charge will be -1 because you need one more negatively charged electron to become 8. Another example, if you're in group 6, you need 2 electrons, so your charge will be -2. If you're in group 5, your charge will be -3. If you're in group 4, you could be +4 or -4. So let's swap this. So here's sodium. He gets chlorine's +1 charge. You only swap the numerical value of the charge. And then here's chlorine. Chlorine gets the 1 from sodium. This one goes here. and this one goes here. When it's both the same number, you can divide them by it and it's the same difference, so you don't write them. So in chemistry, we don't write ones anyway, so the molecular formula is NaCl. Let's look at a second example of how to draw the Lewis dot structure. So the plus ion and the minus ion, they combine together because they are now attracted to each other with the electrostatic attraction. This leads to the ionic bond. So the metal gives an electron to chlorine, and the metal becomes a plus ion, and chlorine gets that electron and it becomes a minus ion. Now they say, oh, I find you attractive, let's hang out together. That is the ionic bond. So when you draw Lewis dot structures, you should draw it like this. Sodium Lewis dot structure is this, and the valence electrons of chlorine has 7, and then sodium loses that electron and becomes a plus 1 ion. In ionic compound Lewis dot structures, the metal has always lost its electron and the non-metal has gained extra electrons. And they both have charges shown here. Metal always has a plus and the non-metal has a negative charge. The charge depends on how many electrons it has gained or lost. An electrostatic attraction between two oppositely charged ions result in the formation of an ionic bond. So these single NaCl ionic bonds, they can attract neighboring ions like this. So this Cl is attracted to this Na, and this Na is attracted to this Cl, and so on and so forth. Like this, you can make a complex structured lattice structure. We draw it like this. This is the expanded version of it. And you can also draw a compact version of it, like when you eat table salt crystals, a kosher salt, they look like this. A tiny piece of it will look like this if you can see the atomic structure. So this whole thing is called the crystal structure, and each of these is an ionic bond between a chlorine and a sodium ion. And remember that cations are much smaller than their parent ion, and anions are much larger than their parent ion. And ionic compounds make crystals due to electrostatic attractions with neighboring ions, like I showed you earlier. Part C, let's look at the formation of a new compound. It's not MgBr2, I'm sorry, it's just MgBr. Magnesium bromide. So magnesium is over here, bromine is over there. Then two different rows in the periodic table. So here's magnesium with 3 shells with 2 electrons since it's in group 2A, and bromine has 4 shells and it has 7 electrons in shell 3. Since magnesium is losing 2 electrons and bromine only takes off 1 electron, you need 2 bromines to obtain the 2 electrons of a single magnesium. So here we go, losing electrons, and now the magnesium loses that and gains the valence electron configuration of the neon element, like that. And then chlorine gets the electron configuration of krypton. Sorry, bromine gets the electron configuration of krypton. So let's look at the criss-cross method to see how to draw the Lewis dot structure. How many molecule atoms combine? So magnesium is 2 plus because it's in group 2A, and bromine is in group 7 and it's a nonmetal, so it needs 1 electron, so it has a -1 charge. We're going to crisscross the ion charge only. Magnesium gets a 1 from bromine, and magnesium's 2 charge goes to bromine. So this is the molecular formula of this compound. 1 magnesium atom with 2 Br atoms. That is what we wrote over here. So when we write it, we ignore the 1 and we write MgBr2. This is the correct formula. And let's now look at drawing the Lewis dot structure for this guy. So now this guy has a +2 charge and they come together and they form the Lewis dot structure. And here are their nearest noble gases. And we are going to draw it like this. And then that's equal to the magnesium now lost 2 electrons, and bromines have gained the electrons. You always put the atom that has lost the electrons between the ones that have gained the electrons. And here's what I explained earlier. And here is a crystal structure of what magnesium bromide crystals actually look like. And here's the three-dimensional MgBr2 crystal structure. It's a little bit different than the chlorine. Here's magnesium. Each magnesium is connected to 3 bromines from 3 angles, and maybe another one from the top, like that. So it forms this kind of a structure. All metals have, all ionic compounds have a crystal structure, and they make very solid crystals at room temperature. Now let's look at predicting the formula of aluminum and oxygen. Pause this video and try to do it on your own, the way we did the other two. Okay, so here's the crisscross formula. Aluminum is in group 3, so we're going to write 3 plus, and oxygen is in group 6A. It needs 2 electrons, its charge is 2 minus. We are going to give the 2 of oxygen to aluminum and the 3 of aluminum to oxygen. So we need 2 aluminum atoms combining with 3 oxygen atoms, and the formula is Al2O3. And how do you draw it? You're going to draw 3 oxygen atoms with spaces in between, and you're going to put the aluminum atoms in the middle, like that. And they're going to lose the electrons like this. And each aluminum is going to give 3 electrons to 2 atoms of oxygen. And then aluminums get a +3 charge and oxygens get a -2 charge. And this is the Lewis dot structure for Al2O3. I want you to go home and practice some of these. And now aluminum has neon's electron configuration, and also oxygen has neon's electron configuration. So part 3, let's look at naming ionic compounds with monoatomic and polyatomic ions. So these are the rules for naming both kinds. Cations always are written first, followed by the anion. If it's formed by a monoatomic ion, then the metal atom name is written first, followed by the non-metal atom name, ending with an "ide." For example, Mg2 plus and O2 minus, magnesium and oxygen, you write MgO and the name would be magnesium oxide. It ends with an "ide." Number 3, the cation is, if it's in the D block, a transition element, since they have many oxidation states, each of them can make many different ions. I talked about this in the periodic table unit. Then we have to specify which oxidation state it's in using Roman numerals inside parentheses. And you put that after you write the metal name in the written name of the compound. For example, if I give you zinc chloride like this, you know this 2 came from zinc. And since there is nothing here, you know a 1 came from chlorine. You do reverse crisscross. And then the formula name would be zinc within parentheses 2, because this 2 came from zinc, chloride. And if you have ZnCl with 1 and 1, then this is zinc 1 chloride. Zinc has a +1 and +2 oxidation states. We will do some practice questions in a bit. If it is formed by two polyatomic ions, you write the first ion name followed by the second ion names. We are not going to be bothered about ides added to the end of the anion name. Example, NH4 plus ion combines with CH3COOH minus ion. This is called acetate and this is called ammonium. So we just state the names of the compound as the ions. So this is the compound form. Because they are both +1 and -1, you just write them as they are. And the name of this is ammonium acetate. Note the number of atoms of each compound like these. We didn't say nitrogen tetrahydride or something like that because that's only used for covalent compounds. So I want you to pause this and see if you can predict the formulas using crisscross and then write the names using the convention, the rules I showed you earlier. Okay, let's try this. This is SRF. This is +1 and this is -1. And this is Na +1 and this is O2 minus. So the 2 goes to Na. This is going to be Na2. And this is +1 and -3. So Li3P. Calcium is +2 and carbon is +4. This is something I want you to pay attention to. So these can be divided by 2 some more. So you can simplify it some more. So the formula would be Ca2C1, which you write as Ca2C. And the same with barium and silicon. Barium is +2 and silicon is -4. So when non-metals or metalloids hang out with a metal, then metalloids take the non-metal side of themselves because the other partner is more metallic. So here barium is 2, silicon is 4. This is going to be 1:2. So it's going to be written as Ba1Si2, which we write as BaSi2. And then cobalt, now these are transition elements. Cobalt is a +2 and chlorine is a -1. Anytime I give you guys transition elements, I will give you the oxidation or the ion state of it because you wouldn't know what it is if I just give you CO. So this guy, the 2 goes to chlorine and chlorine's -1 goes to cobalt and you get COCl2. And iron has multiple oxidation states. So this is iron 3 state and this is sulfur which has a -2. So they crisscross and iron gets the 2 from sulfur and iron 3 goes to sulfur. And here are their names. This is strontium fluoride, sodium oxide, not disodium oxide. You would only say that if it was a covalent compound. And this is lithium phosphide, calcium carbide, barium silicide, cobalt chloride, but you're going to call it cobalt 2 chloride. Remember that. And this one is iron 3 sulfide. Okay, let's look at how the chemical formulas for polyatomic ions and their names. So here is a chart of common polyatomic ions. I would like you to memorize this, but in your tests, I will give you a printout, copy of this electronically. So these are all the -1 charged polyatomic ion formulas and their names. And here are the -2 charged polyatomic ions and their names. And here are the -3 charged polyatomic ions and their names. And note that there is only one positively charged polyatomic ion. So this guy would be written first, followed by any of these other guys. You can also make polyatomic and monoatomic ion containing compounds. Let's look at some examples. So if you want to combine ammonium ion over here, where is this guy, with phosphate. You're going to write ammonium first, followed by phosphate, and you're going to get this compound. And this is very important to remember when you have multiple, this 3 is going to go to ammonium, so you have to put a parenthesis around the ammonium ion before you put the 3. So this is Mg and SiO3. So you're going to put, Mg is going to give a 2, and they're both 3, 2 and 2, so they cancel out because it's 1:1, and you just write it like that. And aluminum and carbonate, the carbonate gets a 3 from aluminum, and once again you put brackets around the carbonate before you put the 3, and aluminum gets the 2. And this one is 1, and this one is 2, so sodium gets the 2, and bicarbonate or hydrogen carbonate does not get parentheses. And then beryllium and manganate, manganate ion is -1, so beryllium gets 1, and beryllium-2 goes to the manganate ion, so you put parentheses. And titanium and copper are group D block elements, transition elements, so it doesn't matter over here. Titanium-2 goes to nitrate within parentheses, and copper gets a 2 from sulfate. And this is how you write their names. This is ammonium phosphate. We don't say triammonium phosphate, you just say ammonium phosphate. This is magnesium silicate, aluminum carbonate, sodium hydrogen carbonate, also called sodium bicarbonate, baking soda, beryllium permanganate, titanium-2 nitrate. Don't confuse nitrate and nitrite. So nitrate has 3 oxygens and nitrite has 2 oxygens. By the way, any of these polyatomic ions with multiple oxygens are called oxyanions. They're always negatively charged ions. And then copper 1 sulfate. And now let's look at properties of ionic compounds. They form crystalline solids at room temperature, as I've shown over here. This is like the pink Himalayan crystal salt, halide, and generally have high melting and boiling points. When dissolved in water, they form electrolytes, and if you dissolve an electrolyte in water and you connect a circuit, electricity will flow through because there are free electrons moving around. And then if you melt a solid crystal or in a liquid state, they also conduct electricity. They are also hard because they have that crystal structure. They break into pieces of the crystal structure, becoming brittle. A review. We looked at how polyatomic ions are formed by electrostatic attractions between a cation and an anion, exchanging electrons, monoatomic or polyatomic ionic compounds, and how to name them. We learned how to predict chemical formulas of monoatomic and polyatomic compounds using the crisscross method. We looked at lattice energy for dissociating ionic compounds, and lattice energy is the energy required to dissociate 1 mole of ions from an ionic compound. And once you dissociate those ions, they go back to their neutral atom states. Electrolytes are solutions of ionic compounds made with water that conduct electricity. And we looked at the properties of ionic compounds. They have high melting and boiling points. They conduct electricity in the liquid state or when dissolved in water. And they are solid and they are brittle. That's it. Thank you. Do your exit ticket.